Thank you. Thank you all for coming to my talk. Yeah, this is a very impressive hall. I've never been in a hall this big. Yeah, but first of all, I'm going to try to take another picture because just now Martin helped me take one, but that was before everybody came in. So now I don't know if I can get all of you, but I'll try. So, yeah. Okay. I'll have one more. Okay, thank you. So I'm going to be tweeting too and tagging it here. So again, thank you so much for coming to my talk. As folks are coming in too, I'll just give a bit of an introduction about myself. So my name is Mary Grygleski. I mean, as such, I'm not originally from Poland, even though I have a Polish name, but it's actually family, so my in-law side. And I'm from Chicago, and I'm a developer advocate at IBM. That's by day, my day job. And then at night, I'm by night, I'm a Java user group organizer in Chicago. So the Chicago Java Users Group, or a short name, we call it CJUG. So I'm very much into community. And also I run a couple of IBM-sponsored meetup groups too in Chicago. So if you ever come to Chicago and looking for a good technical meetup group, please do look us up there. So today I'm going to be talking about reactive. The title is called Reactive for the Impatient, but what this really is so really a gentle introduction to reactive programming and reactive systems. So with a survey of 4 popular reactive Java tools and libraries, so namely RxJava, Spring Reactor, Akka, and Eclipse Vert.x. Can I just see a quick show of hands? I know maybe it's harder for me to see, but I can tell. How many of you are already using reactive programming or systems in your daily work or familiar with it? Yeah. Okay, so it's actually I can tell too, quite a few of you. So thank you. So just to give you a pre-warning is that this will be more of an introductory level. So if you find it a little bit too easy or too basic for you, so you are welcome to not stay too. So I will not be offended, but I just thought I'd let you know. So as such too, I'm trying to make this talk a little bit more interesting in a sense is that I won't go very deep into all the deep dives of technical details because it's just an overview of reactive programming and reactive systems. So let's start. So first of all, why reactive, right? Why all of a sudden we're hearing a lot, maybe within the past 4 or 5 years, a lot of reactive keyword, buzzword coming out in industry newsletter, in the marketplace, all these write-ups. So as such, reactive is not new because let's say, for example, actor model, that's actually very much like the model that's used by the Lightband Akka framework. The actor model actually came out of Erlang in 1980s, and that was actually to meet the demands for real-time telecommunication systems. So that's really, the actor model is really really good in terms of handling events and handling failures and dealing with the fault tolerance of it. So now reactive too is coming out, and so let's explore reasons why it is becoming such a popular thing. Okay. So as we know too, within past 10 years or so, we see a lot of explosion in the hardware side of things. CPU clock speed has greatly improved, and their CPU itself are multi-core, all these amazing hardware advances. And not only that, not even on just hardware level, but on the virtualization level too. Now we're here about cloud strategy, multi-cloud, all these things that come out, hyper-threading in Intel's symmetric multi-processing machines. All of these is basically allowing the software to slowly start to take advantage of the hardware. So then basically right now the software is slowly coming up to speed to kind of take advantage of this hardware advance. And then not only that, there's also on the systems application level too, there are demands of us human beings. Now think of how when we first started, with computing, or even with cell phones, and it used to be maybe one family has one cell phone, but now look at not just one person has one cell phone in the family, but one person has multiple devices. So then it makes it really important now to have a very responsive way of computing to handle all of this requests that's going to the network. So now that's on the system, on the software application level. And ultimately, too, what it is that us human beings, we are truly impatient people. We won't, when we kind of have a request to do something, we won't say, I want this, and you just talk one-track mind. You have multiple requests coming in. Think of your family of a few people, right? Your young children, everybody wants things right away. Everything needs to happen in a very asynchronous fashion. There shouldn't be like a delay in response. And essentially, that's what it is that drives software to kind of come out with constructs that more mimic what the human being, our whole human being culture will need. So that's why, too, I named my title Reactive for the Impatient. Really, it is building for us impatient human beings. So now let's take a look then into what is reactive. First of all, on the reactive systems level, it comes out of a manifesto. Maybe a lot of you have already heard of, especially those of you who are already working with reactive systems, the Reactive Manifesto. This one, it actually is led by Lightband, the company that's headed by one of the founders, Martin Odersky, who's inventor of Akka or Scala, and too. So this company, they also make Akka, this highly reactive systems. So they come out, they are leading this effort of defining a manifesto, providing a set of guidelines to define what reactive systems should be. So here, I won't go into all the details, but you are welcome to also to visit this link to the reactivemanifesto.org. And currently it's at version 2.0, and that came out in September of 2014. And it promises more flexible systems that are highly responsive. That actually, it means that requests come in, and there shouldn't be a wait, too long a wait time for the responses to come back. And that's what essentially the crux of reactive systems should be. And then not only that, too, for requests coming in to have responses, even for failure situation, situations in which you need to recover, the recovery part should also be responsive. You shouldn't be waiting too long for some failure to happen and then be recovering from it. So the handling of failure is also a very important part in a properly designed framework, like reactive framework. So essentially, that's what it is. But let's also then take a look into the 4 core principles of reactive systems. So first and foremost is basically the responsiveness of a system. Actually, this isn't showing. But anyway, so you see that it's responsive. So by being responsive, again, it means that requests coming in and the response needs to come back in a very timely manner. You shouldn't need to wait for it for too long. So basically, responsiveness is really cornerstone of usability and the utility too. It really means that problems can be also detected quickly and dealt with effectively. So, and then that's responsiveness. So that's the core of it. And then there's also the elasticity side of things. Elasticity, it means that if requests coming in, the systems needs to be able to alter the resources in order to meet the demands that comes in. So if there are more requests coming in, you need to either have more resources to handle the requests or have some way of maybe slowing down the requests coming in. So that's what it is. It's the elasticity of it. Although at some point, if the requests are slowing down, then you need to return all of these resources that were allocated to handle processing that needs to go back to the pool or go back to handling some other systems. So that's what elasticity is. So that overall, the overall throughput of a system should not suffer under varying workload is what elasticity is. And then another big thing, a cornerstone of the principle is the resiliency. So resiliency is really achieved by replication, by containment, isolation, and delegation. So failures, it really means is that in any good reactive systems, failure condition occurs. So again, it goes back to that responsiveness too. The handling of the failure situation needs to be happening right away, and so that people don't need to wait. So essentially, that's what it is. And then basically, then you can have part of the system fail and then recover without compromising the whole, and that's what essentially it is. And then all of these 3 kind of core principles are actually hold on a sec. Sorry, I can't get to it. Okay, well, okay. I think I'm a little bit too much. Go back. Okay, so all of the one more like core principle of reactive systems is the message-driven side of things. So it's really message-driven. It's really the mechanics of like being like the mechanics, meaning it's what is enabling the three other principles to happen: the responsiveness, the elasticity, the resiliency. Because message-driven essentially like allow a system of components that are running in isolation to be able to communicate with one another. So that's what like message-driven is. So that's also like very important like core principle of our reactive systems. That allows essentially event-driven systems to happen, as well as for the system to function in an asynchronous, non-blocking way. So that's message-driven. Okay, so now let's also take a bit like look at some clarification too. I'm using a picture of some fruit. So here the fruit, if you look at it, they are all fruit, but actually they are different. So likewise, we're looking at reactive programming, functional reactive programming, and reactive systems and architecture. So all these three are different. Now also too, another thing which I didn't mention earlier is the React. So React JavaScript, that's JavaScript framework coming out of Facebook. So that's different. So I just don't want to like, mingle that in. So I'm talking specifically in this case like for Java JVM systems, reactive. So in reactive programming, what drives the logic forward is basically the events, right? The events, if there is a change in state of this data, that's what drives the whole system forward. That's the logic that's the logical flow. But whereas in functional reactive programming, we write the code in functional style, which many of you are familiar with, I'm assuming, right? So that's functional programming. Now that's different. Now how different is because what drives the logic forward is really the thread of execution in your code. That's what drives it. So again, reactive programming is basically the change in the state of the data that drives it forward. But functional reactive programming is the change in, it's basically the thread of execution that drives it forward. And now when we look into reactive systems and architecture, we are talking about systems that are on a different level of reactivity. We are not just dealing with maybe one component of reactive programming. We are talking about system as a whole. There are many components that they need to kind of synchronize in some fashion. They are all isolated, but they need to be able to basically function together in a very kind of coherent fashion, and that's what reactive systems and architecture is. Okay, so now, then also let's take a look into differences between event-driven and message-driven. Earlier, I talked about one of the principles of reactive systems is message-driven. Yes, that is like the core principle, but yet we're also talking about event-driven. So what are the differences? So here, if you look into this picture up there, event-driven is essentially like messages and events get kind of emitted out of local components. And it doesn't have an address telling it where the message should go to. So as you can see here, and also in reactive programming context too, we're talking about observables, right? Observables come out, events come out. There are some messages, much like the older Java messaging systems, pubs up kind of fashion. You publish some messages, comes out. It doesn't tell it where to go to. It's really up to those who are interested, the observers. They are the ones that are interested in these messages, and they react to it. So that's what it is. You see these little people there, and they are the ones that are observers, observing what events get emitted. Whereas in message-driven, we're talking about messages that have a set address that it needs to go to. So it's much like two people talking, or maybe an envelope. Even if you've worked with SOAP systems, right? They are SOAP envelope. The envelope tells it where to go to. So basically, we're talking about messages with a destination where it should go to. And then it's essentially between two, in this case, it's like two people talking like that. So that's like fundamental differences between the two. Okay, so now we come to the next slide. Over here, I know it's almost dinner time, so it's just so I know earlier I talked about some of these more concepts. They are kind of boring. Some of you are probably thinking, oh, I already know, why do you want to talk about, it's kind of boring. So anyway, in my case, because I first started working more with reactive systems when I started at IBM about 9 months ago. So I was looking at it, it's kind of confusing, and also question as to like what would be good test case to use reactive kind of systems or use reactive programming. So as a developer advocate, I traveled to different countries. So I was actually in Japan, and if you have been to Japan too, you go in and you go into a noodle shop. That's very common. So you need to like place your order and everything, but I won't go into detail now, but I just want to kind of pique your interest, and so then it's not as boring for this talk for you. So I just want to say this will be a good test case. I was just kind of thinking. So just keep that in mind for now. So now let's kind of go back to a bit more talking about like reactive programming. Some of the patterns and terminologies that are associated with reactive programming. So about reactivity. So when we talk about reactivity, it's really the process of responding to stimuli, some external stimuli. There are events that comes, you need to respond to it, and they are like propagating events that you need to respond to it. That's really the process of responding to that. And then for events are the ones that are stimuli. They stimulate, that expect some action to happen to respond to it, basically. And then we a lot of times too, like we talk about streams too in reactive programming. That's also becoming kind of like a good companion. When you deal with reactive programming, reactive systems, you always naturally think of streams. And streams are really primitive representations of a sequence of data elements. So when we talk about getting into nuts and bolts, really the streams are the kind of fundamental building blocks for reactive systems. And again, just now I talked about observables. So observables are really a stream of events that we're talking about. And some of the design patterns in Java design patterns that are commonly used are observer, composite, and iterator. But I won't go into detail for now, just want to point out to you. Okay, so let's explain a bit more about streams. And I'm borrowing some diagrams from the reactive extension, the marble diagram. So over here, when we talk about streams programming, basically think of it, it's less like traditional style. We're talking about declarative style of programming in here, that we're dealing with timeline. So think of like streams are like a timeline. Like think of it, this is a four-case scenario. These are basic diagrams of streams. The very top one is basically a stream without any events on it, so just a stream kind of waiting for some events to happen. Then the second one is basically you see some marbles, it represents some events, some data that comes in. And then over there, then at the far end of the second one, you see like a perpendicular line. It means that the stream has a definite time expiration to it. So it expires, it finishes its job, and it ends, it terminates. And then the third one you see is that some events happen, then you see like a cross. The cross represents a failure event. So in reactive programming, the failure events are like first-class citizen, so to speak, which means that unlike traditional programming, in which when you do the older traditional way imperative style of programming, you do try-catch to catch error exceptions. But here in reactive programming, failures are just another event that requires the consumer to have to do something about it. So that's what is being represented in streams programming. And then the very bottom one is another stream that has events, but then there's nothing else because this is an open-ended stream. It's still like remaining open for any events to come into in this case. So now then take a bit look too into an example in coding too. So here I'm using the operator map. So map is basically a transformer. It transforms the data that comes in. We're talking about functional style of programming. So here, you look at the top line, that stream has some events that happen that carries with it data individually. So you see there's like 1, 2, and 3. And then what we do in here is that we apply that transformer, do a dot map. So the dot map is basically telling it to multiply by 10. And then if you see that after transformation, then the result in the bottom one, you see like 10, 20, and 30, because then you apply the transformer, then each one of them gets multiplied, all the data gets multiplied by 10. So if you look into the code, then using RxJava syntax, we're using an observable, doing a dot just. The dot just is basically taking that input. In this case, we're hard coding 1, 2, and 3. And then you do a dot map, and that applies the transformer to it. So multiply everything by 10 that comes in. And then you immediately subscribe the client, basically client, the consumer, subscribing to the producer right away in here within the same command statement. So then over here, what it does is basically just print out. Doing a timber.d here is just sending the result to the system output console. So then you see the output to the right-hand bottom here is item 1 becomes 10, and then item 20 and 30. And if you would like to see more examples, you can also visit this rxmarbles.com. It allows you some interactive kind of playing around with some of those operators too. For example, map is just a basic transforming operator. Then there's also like flat map and filter and sorted and some of these other operators that you can try out too. So one thing just want to point out is that you can also now look at, if you haven't worked with reactive style of functional programming, is that it's actually very elegant. Because think of in a traditional imperative way, if you want to have like input that comes in, then you need basically your program needs to have multiple statements. First, you read in what's coming in from the command line, then you need to parse your input, and then analyze, and then basically then apply your transformation, and then another command that basically say print. But in reactive style of programming, you can see everything is all done, they chain together, so to speak, like pipeline together into like one command statement. So that's a really like more beautiful and elegant way of doing programming. And of course it has some drawbacks too, but we will go into it in a little bit. And also, just want to like echo one of our masters of our time, Venkat. Venkat has actually pointed out, if some of you have been to his talk, he has pointed out, he is kind of giving a visionary talk. He is saying that reactive programming could become like the future of programming too, because of just how elegant it handles on a syntactical level too. Okay, so now after talking about reactive programming, I'd like to talk about reactive systems design, some of the patterns. So in reactive systems, we're basically taking reactivity to another level. Then in this case, we have to deal with the systems, like multiple components. They each are functioning on their own. And for example, like microservices systems, right? You break up a big monoliths into small pieces. So the reactive systems, that needs to be designed in a very good way that has all these patterns that enable, for example, here that I highlighted some patterns here, state management and persistence systems, flow control system patterns, and message flow, fault tolerance, recovery, replication, and resource management pattern. So some of those patterns that you might have worked with, for example, like in state management, there are like event sourcing and event streaming, sharding. Those are like state management patterns. And flow control patterns like pull and drop and throttling, those are like controlling flow. And also message flow pattern like request responses, self-contained messaging. Fault tolerance recovery patterns like the back pressure and circuit breaker. And replication too, there are patterns in there, and some resource management patterns. So there's also a book that is written up very good and describe all of these individual like patterns in details. It's called Reactive Systems Design. I have the link of that book towards the end too in my slide, if you're interested. Okay. And now let me also talk a bit more about reactive systems design. So in reactive systems, we're talking about reactive microservices versus monoliths. So in today's world, we're talking about app modernization. So we're breaking up systems that's traditionally maybe one JVM that houses all the functions in it. Let's say in an e-commerce systems, you're running an order entry subsystem inside the same JVM, or still like shipping subcomponent, everything in the same JVM. So you can see it actually can be very brittle. Anything happen to one subsystem, it can break the whole thing. And if you want to upgrade one small component, it may not be that easy at all. You have to bring down the whole thing and then do all that kind of upgrading. So basically, reactive, or you're breaking the whole monoliths into small microservices, subsystems, and they each kind of have specific functions. It makes the upgrading a lot more easier to maintain, for example, and develop too. However, also bear in mind too, breaking things up into different microservices has its challenges too, because how do you do the monitoring, right? The logging is just becoming more difficult. The operational side is more complicated, which is nowadays though, with cloud computing, all of these more like the logging and all of these distributed metrics, that's actually making it a bit easier to kind of manage microservices systems. So going back, like reactive microservices are basically you're applying reactive principle to your microservices, doing like asynchronous and non-blocking type of coding construct in your code. And so when we talk about reactive systems, we are also basically talking about the isolation of state, space, time, and failure in a system. And again, I just want to point out circuit breakers. Circuit breakers are essentially, if you have failures coming into your system, the failures cannot be to keep propagate throughout the life cycle of your system too. It needs to be handled right away, for example. And then there's also like back pressure that in reactive systems, that basically back pressures are essentially like too many requests coming into a system, and basically the system cannot handle it in some way. So a very good reactive systems ought to have capability of handling these requests coming in. So it's either slowing down the input, or basically it's like the elasticity side of things of your system should then have more, basically it should have more resources then to handle all these requests that are coming in. So the back pressure is a very important thing inside like reactive systems. And then we're also talking about in reactive systems, there are high availability and eventual consistency. And in any kind of like data-intensive systems, basically, here too, I highlight this CAP theorem. So if you're familiar with that, it's basically CAP theorem is talking about data-intensive, any kind of data-intensive systems. So any data systems will have three aspects to it. It's the network partition, and also the high availability of these data, and also the data accuracy of the data. So the CAP theorem basically is saying is that of the three principles of any data-intensive systems, only two can coexist at any time. So basically, in this case, the network partition, meaning the connection to the network, it's always true, because then you need the systems to be connected, and you get your data in. So in this case, then it leaves the high availability and consistency of the data. And in this case, one of them will need to like relax a bit. And so basically, in order to satisfy reactive systems principle, the responsiveness, basically high availability needs to always happen. You always want to have data be highly available, which means then your consistency of your data can suffer a little bit. But that doesn't mean, too, the data will always be inaccurate. For example, like except for maybe like high-frequency trading systems, actually reactive systems might be good. Like say, for example, in an IoT application, you have many data coming in, and because you want to have the data be very responsive, then you have the high availability. But the consistency aspect, you can relax a little bit. So sometimes the data comes back could be a little bit not quite accurate, but that's okay. Because if you keep querying a system, eventually they believe the data will become consistent and accurate. If you kind of keep querying, and at some point it will be consistent. So that's what like CAP theorem is. So anyway, in a very good reactive systems, it needs to have very good patterns and like construct and mechanism to handle this aspect of data systems. And Akka systems actually pretty good with the actor model of having all of these patterns managing it quite well. So, okay, so another thing about reactive systems I want to bring to your attention is the reactive streams specification. So this reactive streams essentially is a standard for asynchronous stream processing with non-blocking back pressure. And basically, it's currently the specification is at 1.0, and working group started in 2013. It's led by Lightband, and Netflix and Pivotal also joined, and then Oracle, Twitter, Red Hat, all of these major companies. So right now, RxJava, the reactive extension, is supporting reactive streams, although the 2.0 may not be supporting it fully. But the Spring Pivotal, the reactor, is supporting it fully. And then there's also Akka, which supports it fully as well. So that's reactive streams. And then what about microservices? Let's going back a little, talk about microservices. So reactive programming is basically used within a single microservice. It's used for implementing service internal logic, and it manages the data flow. But reactive systems are basically used in between the microservices because of its message-driven capability. So then that enables the system as a whole to have the responsiveness, the resiliency, and elasticity of a reactive systems. And here, I want to also point out a reactive microservices framework that comes from Lightband. It's called Lagom. And this one comes from Lightband. It's built on on the Play framework, which is a front-end framework, and Akka cluster from Lightbend. And it has RPC style of programming, and also it has a message broker API that's implemented in Akka streams and Kafka too. And there's persistence base is on the concepts of domain-driven design. And there's event sourcing and CQRS, which is the command query responsibility separation. This I won't go into detail, but I just want to point out to you. Okay, so now I'll go back to that use case that I pointed out earlier with the noodle shop. So here, I just want to quickly kind of point out to you. So in Japan, when you go inside a noodle shop, basically there isn't a waiter or waitress to take your order. You basically have to use a vending machine to punch in your order, and it's all in Japanese as well. And so it was hard for me because I don't know Japanese. And I remember I was inside, and actually, first of all, you go in, only one vending machine. So the line can be very long during lunchtime or dinner time. Then you line up and you punch in your order, and then you put in your money, and it only accepts cash. And then you get your ticket. Then with the ticket, you then give to the server, and then they will go and prepare your noodles. Now, as you can see over here, too, everybody eats around like a bar area. That's where the kitchen, where they prepare all the food. So you can tell, too, there are no tables or chairs, so you have to essentially wait in line. For that time, I was waiting for 40 minutes before I can get a table, or not a table, it's just a seat, around the edge to sit down and eat. So immediately, too, when I came back, it was back in December, around Christmas time, I was thinking, that might be a good thing to kind of use reactive programming style to design a system for it. So here, it's just something I translated into this paper because I was kind of thinking and scribbling on a napkin. So I was thinking, well, maybe we can kind of design a system that basically takes order in a mobile app, right? The front end of mobile app. So it's kind of, think of it, this system, essentially, everybody, you can download your mobile app, so your customers is right there. The customers coming in, place the order. So the order is an event. So the event is essentially the observables in reactive computing terms. So you place your order, you got your observables, and basically who is observing would be like the waiter at the other end, waiters or waitresses at the other end, the service people. And so they are looking at, their order's coming in, however, they can't really tell the cook to cook it yet because we need a seat for the customer to come in to eat. So we will need then another observable streams, right? That one is essentially will tell if there's a seat available. So if there are seats available, then you get also the observables as an event that the seat is opening up. And so now the observers for these two observables, the waiters or waitresses, they will have to make sure that you have an open seat, and then you take an order from your observables, and basically then with that you construct an order. Then that can be given to the cook to basically cook the ramen noodles. And then at that point too, then you can see when the cook is cooking the noodles, and basically when it's ready, then it will be another event that comes out. It's basically telling that the noodles are ready. And it will then notify us, right? We place the order, so we're real hungry. Basically, it's kind of, we are the observers now for waiting for the noodles to be ready. So essentially, it's a very simple example. It's probably not exactly very accurate, but just gives you an idea. It's just a concept, right? We can kind of design a system like that. So you can tell why reactive systems would be useful in this case, because it's essentially, it's non-blocking, it's asynchronous. So think of it's really mimic what us human beings are. We don't want to wait. Say we are busy programmers. We have our time are precious. We're doing all the work. It takes a lot of energy to think about that. So instead of waiting in line it's a block, in computing terms, it would be, the traditional way would be blocking. You are just waiting in line, punch in your order. You even have to wait in line to punch your order in, and then you wait for your table and sit down and eat. So think of if we have a system that's on a mobile app, it's really reactive kind of way of doing things. You basically, pull up my phone and punch in my order, and basically then you enter your order into that. You're just essentially waiting for notification to come. Just think of how much time we can save in this case. It becomes a non-blocking type of operation. You issue your order on your phone, and then you just basically gladly go on your way. You're still programming, doing your thing. And then when it's done, it's basically maybe almost done, then the waiters or waitresses on the other side will say, hey, your table is ready, your food will be ready in 5 minutes. So at that point, you can say, hey, good, I have 5 more minutes, so let me finish, maybe issue a compile something that will do my programming. Now I kind of put on my shoes, and then I'll go downstairs and cross the street to go eat my noodles. So think of, like in reactive systems, in some ways, this is a good example of how you can apply this principle, this style of programming to design a system that's useful. And also, too, another thing now it brings to mind, too, which I didn't put on the slide. I was also in India, in Bangalore, in April. And if you have been to India, it's actually very interesting. Their traffic system, on the road, there's no traffic signs. There's no traffic lanes. So you can imagine, in order to try to cross the road, it becomes kind of like a reactive systems in computing terms. Because then you have to basically watch for cars coming. They are all independently, vehicles and things on the road. They are cars. They are like little tuk-tuks. They are like little tuk-tuks. They are kind of like a 3-people little motorcycle thing. They are big, vans and big buses. They are like all running on the road. But then in order for you to cross the road, you have to basically dart across the street and look for, okay, there's a gap. Then you kind of walk and run across. And think of it, in some sense, it is also like reactive programming, because it's like you need to be reactive too, and then there's also back pressure built up if you hold the traffic on too long, and basically you have to dart across the street and go to the median street strip and then wait for the other side, all the traffic to go. That's, in some ways, is also like reactive computing in some sense. So I just thought I'd give an example to you. Okay, so now I think I have about 13 minutes left. So I'll go into then talking about the 4 commonly used Java libraries in the reactive landscape. So first of all is RxJava. So RxJava is really a Java implementation of the reactive extension. That's actually reactive extension was started by Microsoft. It's actually Rx.net that came out first. And it became real popular. And then Netflix, in 2013, they were then interested in porting this reactive extension to Java, which they did. And so version 1 came out in 2014. And Rx has become very popular, too. It's also available in JavaScript, so that's RxJS, and then also in Scala, Clojure, and Swift, too. And currently it's at version 2 that came out in 2016, and it's suggested to use version 2 and not like version 1, because 2016, that version has flowable and has support for back pressure as well. So let's take a quick look then at some sample. This one is just a hello world example. So again, using the functional style construct, you can tell using a hello world becomes a very elegant way. You can pipeline your commands together in one command statement. So over here, you're doing a flowable. The flowable then do a dot from array. You take in the argument from the command line. So inside will take care of the arguments, and then you do an immediate subscribe. The subscribe essentially will just do a system out print line and print out hello world in this case. So as you can see, it is a very elegant style of programming. Okay. So. And this one, too, is another example. This is less of really a program, but just wanted to show you, which I already showed you earlier, too, is that essentially, over here, just wanted to show you the producer is the observable. So you do a .just, and it takes in the input. And the consumer, in this case, is just a system out print line. And so in order to attach your producer to consumer, all you need to do is just do an observable.subscribe. So subscribe will basically just pass in the consumer, and that's how you attach the two together. So that was RxJava. So now let's turn to Spring Reactor. So Spring Reactor came out of Pivotal. It's based on Project Reactor, and it's very similar API to RxJava 2. Because the two engineering teams, they actually work together on both framework. That's why it's very similar. But for Spring Reactor, it came out since Java 8. So it makes full use of the Java 8 streaming and functional style of programming. So it gives a more cleaner interface. And here I just gave a quote to David Karnock, who is the project lead for RxJava, also contribute to the Reactor. He says, use Reactor 3 if you are allowed to use Java 8 or higher. And then use RxJava 2 if you're stuck on Java 6 or need your functions to throw checked exceptions. And here, too, for Spring Reactor, I just list out a bunch of libraries, but the main one to use is Reactor Core. And you can see, too, it also has very good integration, like with Kafka, with the other Reactor Adapter, Netty, and RabbitMQ. And also has incubating reactive streams foundation for .NET and JavaScript as well. So here, we'll take a look at another small code example. So here, if you look into using Spring Web Reactive, the non-blocking web stack, the top one, the few lines, is a traditional approach using Spring MVC. So over here, you look at like get all products. If you run that, then what will happen? It is a blocking call. They look similar, the two like calling construct, but actually the Spring MVC one is blocking. So if you run in the runtime, you'll see traditional way started. And then the next line, it goes into actually call and get the products. So in this case, the list of products won't come back. In the meantime, your method is being blocked. It's blocked waiting for the list of products to come back. When it comes back, then you will see the next line, traditional way completed. Then the whole method will return. So that's the traditional way. Now, if you look into the bottom half of this example, this is a reactive approach using Spring Reactive and the web flux. So over here, you print out system out print line. You first see reactive way using flux started, and then the next line is you go and get product stream, and basically that one will return a flux. Think of flux as like a ticket. You just tell it you want some work to be done, then you get a ticket back, but you actually don't get the list of products yet. In the meantime, then if you run this, you will then see reactive way using flux completed. Now, at this point, the method will exit. But in the meantime, the processing actually is happening behind the scenes. And then your client, your consumer, will hold on to this flux. And basically, when it's ready, it's just function like any other way of like using HTTP kind of way syntax construct, right? Then basically the sync will get completed. Your sync will get all the results, and basically then you can then use traditional HTTP style to get back your results. However, there's also, if you look over here too, there's also an event. If you want to do it the reactive way for your client to actually get back the results in a reactive fashion, you can also make use of an event that's over here. I specified too in your attribute annotation over there, get mapping. There's a text event stream value. That one is essentially allow you to use the server sent for your client to subscribe to the server. I think there's a server source event. I'm sorry, that one I forgot. Yeah, server sent event. So you basically can have your client subscribe to that server sent event, and basically then your client can happily go do something, whatever it's doing. Then basically when the server sent event happens, then it will trigger an action and telling the client that my result is ready. So you can actually also basically have your client kind of take care of your responses in a reactive way, using that. Now that has some drawbacks too, but I won't go into detail here, but I just want to point out too, there are just two ways of how you can, or more than two ways of handling how you can get back the response. So that's Spring 5, the reactor. Okay. Now, that's just a quick comparison between like RxJava and Spring Reactor, which I already went through most of it, but I just want to quickly point out is that basically the reactive stream, RxJava only support reactive streams partially, but Spring Reactor will support reactive streams fully. And basically, Spring Reactor started supporting Java 8, so it has a more cleaner interface to it, too. RxJava came out since Java 6, so you can tell, too, that it's a bit kind of older, so it doesn't also support reactive streams fully, not yet. So, and I have these slides available to you, too, if you're interested afterwards. So, now, I'll go then talk about Akka. So Akka comes out from Lightband, and IBM has a partnership with Lightband, and since June of 2017, so almost like 2 years ago. And again, Akka is basically built using the actor model that comes out of Erlang, and it's the actor programming model came out already in 1980s because of the telecommunications needs. Yeah, like you need real-time systems in like phone systems. And it's highly event-driven, and it also has location transparency. So basically, location transparency is basically, you can just use names to kind of find your resources. And basically, there's Akka remoting that handles all of these, the name like transparency in this case. And then Akka too itself is also very lightweight. And also for the recoverability and resiliency, Akka has a very strong supervisor capability. That essentially draws from the Erlang programming model. So the supervisor capability is that you have a systems running, and basically there's a main actor. That actor will basically be listening for any problems that happen. So then a component, if it's can't handle back pressure coming, it can have a self-healing kind of mechanism built in and notify your supervisor that, well, I'm under pressure, do something about it. So that's a pretty powerful capability in Akka. Here, so I'll just show a quick example then of Hello World using the actor model, and this time it's in Java first. So over here, you can see the main method in here. So the main is basically will create this infrastructure needed for running these actors. And it starts this main, and then basically it only has one command to it. Which it does is it starts out the actor, the Hello World actor. So let's take a look. So in the Hello World, it's the application's main class. So it terminates. When it terminates, then the application will shut down. The main business logic then happens in the pre-start method, if you look below there. So this pre-start method is where another actor is the greeter actor. Remember, too, in Akka is that you have actors that handle different functions within your system, your program, too. So the greeter actor is the ones that actually listen for what's coming in, the argument, and then it takes that and basically then will process that data for you. So in this case, the greeter is done, then it will tell us by sending back a message. So that the message, when the message has been received, then it will pass into the behavior described by the onReceive method. Okay, so let's take a look at the greeter. So this is the greeter method in here. So what it does is that when your main starts, so it starts the Hello World will then start your greeter actor. So when the greeter receives a message, then it will react to it. So basically it complies. It will have you see that there is a onReceive. So what it does is that then it will print out Hello World and also print out what's being passed in the argument. So that's what it is. But as you can see too, the actor model, using Java is a bit more coding because of the needs of writing your code using actors to handle different functions within your program. But as such, it is also a very powerful system too. Okay, I think I only have 3 minutes left, so I'll be a little faster. So here is just an example of this Hello World in Scala. But as such too, Scala by itself is very naturally, it lends itself to an actor model, functional style programming. So you can tell, using Scala, it's a fewer lines of code in here too, which I won't go into detail because the talk isn't so much about Scala, but I want to point out to you. And okay, so now comes to the last library that I want to talk about quickly is the Vert.x. Vert.x comes out of Eclipse. A very powerful feature of it is very polyglot in nature. And so in other words, you can actually mix in. You can have your code, your Vert.x running. It can also interact with, you can put in some JavaScript code or Ruby or any other kind of language patterns. It doesn't matter because of its polyglot nature. And it doesn't make use of any actor model. It's similar to actor model. It's called verticals. So verticals, they are being deployed and executed by the Vert.x engine. And it's event-driven, and it runs only when they receive a message. And there's also a Vert.x event bus that kind of handles all the events that are coming in. And again, it's not restrictively tied to any container. It can be used with other libraries. So it makes it kind of very special. And it's also the newest library among all four. So here is a quick example of doing a Hello World. So in this case, again, it's also very kind of simplified. The whole code, you can write your line, Hello World in one line. So here's what you do. You do a Vert.x and then .Vert.x and doing a .create HTTP server. And immediately then you basically you pipe it and have the request handler that takes in your requests. And basically your response is right there, .end, Hello World. And basically you have a .listen. Basically it binds your HTTP server to port 8080 in this case. So as you can see, Vert.x can be very lightweight, very elegant in its programming constructs as well. Okay, so I think I only have about a minute, but I want to do a quick recap. So reactive is really an overloaded word in today's market, and it's not really for the faint of heart. You know, if you haven't done it before, you may find it a bit confusing, but stick with it, because once you get through it, it's very nice to know how to do event-driven programming. And again, some of these are the benefits that I've talked about, and what are some of the differences. And then one thing I wanted to point out is that the reactivity to this day has not been fully ready on the database level. Now, we have heard too, I think even in this conference too, that Mark from Pivotal talked about the database connectivity. On the connectivity level, there are non-blocking connectivity library that connects to the database. True. There's R2DBC from Pivotal. That one is a connectivity level that's using non-blocking constructs. However, when you get down, your whole system, it gets down to the database level, the database engine, like say Oracle database, they are still using blocking I/O. So in a true sense, there are no true systems that are truly reactive yet in that sense. Even though there's connectivity, you can connect to the database like non-blocking, but gets down to the engine, then you still need to wait for things to be blocked on that level. So that's one thing, just thought I should point out to you. And with that, I think I kind of no time left now, but I do want to thank you all for coming to my talk here. Again, the slides will be available too, but I would like you to invite all of you, if you haven't already done so, is to sign up for the IBM Cloud free tier access. That's like no time expiration too. So that's the tiny URL in there if you want to sign up for that. Just log on to it and play around. There are many different kinds of components. There's also OpenLiberty, which is the free version of WebSphere that you can make use of. There's microprofile, all of these EE constructs that you can, enterprise Java constructs that you can use. Many other things, the Watson, the AI, machine learning, you name it. IBM has it. It's like a giant Lego box. And then over here to the second section here is about our IBM, developer.ibm.com, the reactive systems resources, and also the Lightbend information and the Reactive Manifesto, and also that one book I pointed out, reactivedesignpatterns.com. That has all the description of all of the reactive systems design. And then also one more thing is with our IBM Java newsletter too that I encourage all of you to subscribe to. If you haven't already done so, we have every month we have a newsletter that comes out and provide you with very useful links. There's also OpenJDK, Adopt OpenJDK. These are all community-driven JDK that comes out since the Oracle change of release cadence. The OpenJDK has become more active too, and everybody is encouraged to submit your requests or even participate in the OpenJDK initiatives and contribute to it too. So that's the newsletter. And just a couple of small things is that I like to also invite all of you that to join this effort. It's very worthwhile. It's called Call for Code. It's IBM leading this effort. It's a global, open to anybody. It's a global hackathon. So anybody can join, and it's for natural disaster preparedness. It's very worthwhile. The prize money is like up to $200,000 US dollars. So it's not a small sum of money. So there's like different pricing levels. So I encourage, if you're interested, please take a look into it and sign up for it. Maybe you design a very useful application, an app for like natural disaster preparedness. And it's still open until July 29th. So we still have a little over a month before the deadline. You can form teams of up to 5 people, or you can enter as yourself too and design an application. And I'm not sure if Krakow has any Call for Code like hackathon meetups. But if you follow me too on Twitter, I'll be also posting some more information about this Call for Code. Or just go to the callforcode.org too. It has information about how to maybe join a local Call for Code hackathon too. So that's that. And with that, I think I come to the end. And so I encourage all of you to ask more questions. I think it's always good. And also participate in your community. And I always feel that having a community will really make things more interesting. And you find that you're growing and learning every day. And ultimately, too, it's just, we are all passionate technologists. I'm not here to kind of push and tell you buy IBM or something. But it's just, let's build, a better world. Let's use technology for a good cause is what we're trying to advocate. And so please follow us. And yeah, if you have questions, please follow us and reach out, email, Twitter, however way you want. So and talk about anything. And also, I'm also putting together a virtual user meetup group. It's called Reactive Meetup Group. It hasn't happened yet because it's taking some time to kind of set up all the logistics. But that's my goal, is to set up something maybe during this summer. So then I'm going to run that meetup group, and everybody can participate. The format will be like inviting some speakers to talk about certain topics on Reactive, and also have audience participation too if we want to ask questions or suggest anything or make it better, essentially. So yeah, so with that, it comes to an end, and thank you so much again for coming to my talk.
Thank you very much, Mary! All right.